And then I will also, I have a YouTube channel that I will link in the website.
Yes.
So I put the collection of videos as a course, which I think can be useful because some people have class at this time and cannot follow. So it remains there also in the web page. So people can recover the covering either through the recording, either through the web page where you have the direct recording in Zoom, or I also try to upload them more or less regularly. Yet the last class is not there in the YouTube channel. Today it's an exciting day. I'm looking forward for the class of today because we have Pau and Joaquim who are going to be the stars. Well, I mean, the stars are the students, right? Today. So today I'm going to be like this person in the sofa. I'm going to be watching the others do the class. I have my popcorn ready and I'm looking forward to the class of today to see how it works. So, well, first things, are there questions from the last class? Well, I mean that the people who are now connected really want to go to the list of problems. I'm very happy to know we have several volunteers that have been working hard. And I leave the word to Pau and Joaquim. Go on, guys.
Well, good morning, everyone. Well, I'm Pau and well, Joaquim will present himself now. Just to say that today it's the first problem session of the course. There will be another one on the 28th, and we will abort mainly the theory that Eva presented in the first 3 days of this course in form of problems. We will be solving problems in Poisson geometry and symplectic geometry, starting from a really easy one in Poisson geometry, and then we will go to more complicated one in B Poisson and B cohomology, which we hope you will take advantage because it's the way to clarify sometimes theory that you have seen a lot of theory in only 3 days, and now it's a moment to set it a little bit down. Joaquim?
Yeah, this is Joaquim. So in the list of exercises, as Pau said, you have a wide diversity of exercises. So there are exercises that are designed to be doable right away. And we know that several of you have tried them. So that was great. And there are also exercises that are more high level, just as examples of what we have learned in theory rather than proper exercises. But yeah, you can go first, Pau.
Yes, I will start. Thank you, Joaquim. I will start sharing my screen since we will kind of mix handwriting with projecting, with even if you want to participate at some point and you can handwrite or can project, you will be invited to do so. I will start projecting my screen. And
yes, before I forget, the plan more or less is to, well, Pau will start with one exercise. Then I will do a couple of the exercises at the beginning. And then we'll start taking volunteers if people want. I think that we have one person who will do one exercise right away. And then we can take suggestions if you want particular exercises on the list to be solved. Otherwise, we have an order that we can follow.
So we will start with a problem that was not included in the first original list we posted with 12 problems, but it was already there when we put the second version, the final version of the list, which is problem 113 in the list that you can find now and yesterday and on Tuesday already in the web. And it's this one. It's exercise 113, which is basically to prove that the symplectic form defines a Poisson bracket in this way. Now, if you have symplectic manifold, you can construct a Poisson bracket if you define it the following way. You take the bracket of two functions as the omega applied to the Hamiltonian vector fields of the two functions. So for any symplectic manifold, you can define this Poisson bracket, but let's check that this is true, that you can always do this construction. And we have to check basically the four properties that a Poisson bracket has to satisfy to be a properly defined Poisson bracket. Two of them are direct and quite easy. The third one is quite easy to prove too. And the last one is the one that takes more work to do to prove it. And there are different ways to do it. We'll do it in one way. Maybe you find other ways to do it that are also fine. So we will start by proving the first properties that the bracket has to satisfy. These are the four properties we have to check for this Poisson bracket, and are the following ones. The properties that the bracket has to satisfy, we put bracket of f and g, has to satisfy are the following ones. To satisfy are the ones that you saw in Eva's slides, and are the ones that you for sure have seen before in other courses in Poisson geometry. First one is bilinearity. It has to be bilinear as an operator, since it is constructed from a two form, a symplectic form. It's clearly a bilinear. So bilinearity is satisfied clearly because it's defined from omega, which we know by definition of a symplectic form is a two form, which is bilinear. So it's linear in both components. Is satisfied almost by definition by the bilinearity of omega of the two form of the differential two form, the symplectic two form omega. The same happens with the second property we have to check, which is antisymmetry. And antisymmetry is for free because of the same reason, because omega is an antisymmetric form. It's since it is a symplectic form, it's a two form which is antisymmetric. And we have for free also antisymmetry of the Poisson bracket, which is something we need, no? Antisymmetry. So the fact that the bracket of f and g is equal to minus the bracket of g and f is satisfied by the same result, is satisfied by the properties of omega, which one of them is antisymmetry, by antisymmetry of omega. Symmetry of omega. The third property that has to be fulfilled for this bracket to be a proper Poisson bracket is Leibniz rule. Leibniz rule, derivation rule, classical derivation rule. In this case, for the bracket, is the following rule. You have to have that the bracket of f and g times h equals g times the bracket of f and h plus h of the bracket times the bracket of f and g. We are going to use one of the properties of the Poisson bracket here that by definition comes quite for free too, which is the following one. I'm going to create a new slide here. I'm going to use here that the bracket of f and g in general for two general f and g's is precisely the Hamiltonian vector field of f like on g. This is one of the properties of the Poisson bracket. In one of the ways it is defined, and we are going to use this in order to prove the property we want to prove, which is that f with g dot h satisfies Leibniz rule. So we will expand this this expression. We will arrive to the fact that it is equal to the other expression we had at the start. So by the first line here, we can write this Hamiltonian vector field associated to the function f defined in the manifold applied to the product GH. Now, since this is a derivation, in fact, this is a derivation, and we can write that. I will use another one of the properties it has, which is that we can also write this expression in this form, and we precisely at this point in which this derivation and this Leibniz rule appears and has this effect, because at this point we can write the derivation of the product GH. This is the point where this Leibniz rule will appears. It reveals here, applied to XF. And since we are derivating a product, we know we have to separate H dj plus G dH, these differential one forms that appear here, applied both to XF. At this point, we get back to two expressions, which are a special form of the Poisson vector field that we will also get back. So now we separate the sum in the two terms it has. We arrive to H dg on the Hamiltonian vector field of F plus G dH also on the Hamiltonian vector field of F. And we know that this is simply by definition of this Poisson vector field, of this Poisson bracket. This is H of the Poisson bracket of F and G plus G times the Poisson bracket of F and H. So Leibniz rule is a line, and you can prove it using basically the properties of the differential of the one forms applied on a product. So third rule is satisfied. Let's check Jacobi's identity, which is maybe which requires more lines. And Jacobi's identity is the following one. Jacobi's identity is this rule. It's like a circular relation that the Poisson bracket has to fulfill, which is that the bracket of F with the bracket of G and H, the circular sum, I could write it more in a compressed way with the circular sum, but I will write it like expanded. Sorry, I will change, since in my notes I have it written another way. I will write first this bracket is the same, but I prefer now to write the proof in this form. So we will prove this identity. The circular sum changing the order of F, G, and H is identically 0. So we will prove that if we do first F and G and then the Poisson bracket of this with H, then we do G, H, and F, and then we add H, F with G with the bracket, this sums up to 0. We will prove this, which is a Jacobi identity and which has to be satisfied by this Poisson bracket we are defining. So at this point, we are going to use the hint we have in the exercise. I'm going to show again the hint. We had a hint in this first exercise that we are solving today. We had a hint, which we are going to use here, which is to expand the expression of the differential of omega. Since we're going to use a two form, which is a symplectic form, we know it's closed, we know its differentials will be 0, and we will apply that this differential vanishes when we specifically apply it to 3 vector fields, which come from 3 functions f, g, and h, which are the 3 functions we are talking about. So we will use the fact that omega is a symplectic form, and hence it's a closed form. So let's take this identity and let's check that the differential of this is 0, meaning let's check that this corresponds to this differential applied to the vector fields, and hence it is 0. We will check that it is 0. So let's start by recalling how do we operate when we have a differential of a form, a general form. So let me start a new slide and let recall this following way of computing the differential of a form. Recall how do we compute a differential of a form. Recall that if we have a K form defined in a manifold. We have some, I will call it omega, since we will call it later also omega. If we have an omega, which is a K form, then the differential of omega is computed in the following way. No? The differential of omega will be a K plus 1 form in M. And we can compute the differential of omega in the following way. If let's see how do we compute it, basing the computation on how it acts on K, in this case K plus 1 vector fields. I will use the notation of excluding an index. If I put a hat now in an index, it will be the term that does not appear. And we know that the differential of a differential form can be computed in the following way. We have to sum up from 0 to K. This with this sign, the corresponding sign, this omega applied to all the vector fields, but the vector field in the position I. So we, in this case, have to consider all the vector fields except for the vector field in the position I, which is the one I marked with this hat. This hat means that not included in the computation. I will write it here in another color. I will write now here, which means this hat meaning that the classical notation meaning that it is not included. And there's another term in the sum which accounts for the term that comes with the Poisson bracket. If now we have to add the other term, we have to take into account the Poisson bracket that appears as a combination of any two pairs of vector fields here. So we have this omega applied to the vector, to the K vector fields, including the first one being the bracket, the Poisson, the Lie bracket, sorry, the Lie bracket, not the Poisson bracket, the Lie bracket of any pair I and J with all the other vector fields except precisely for I, except of I, sorry, this will be an I, and except of xj, x up to xk. So in our case, it will be quite easy, quite simple, this formula, since we are applying it to three vector fields. We will use that we already know beforehand that this expression we are going to write here will be 0, since we are going to use the differential of omega, which is a symplectic form, and we will apply it to xf, xg, and xh. This is the hint. It was a hint. We are going directly to use the hint, and we are going to expand this expression thanks to the formula we have here on the top. And we know that this equals, first of all, xf times omega of xg, xh minus xg times omega of xf, xh, plus what we have to take care here is basically the signs, and here it's an alternating sum, and basically we will have signs that will compensate. Sorry, no, in this case, no. We will not cancel each other, so we will have a sum which is not 0, that we know is equal to 0. So any term will cancel with each other, but we know beforehand that the sum is 0. So we will arrive precisely to Jacobi's rule by expanding this expression here. So we have here xf, omega applied to xf, and xh. This accounts for the first sum, and then from the second sum we obtain 3 more terms. First one of it is omega applied to the Lie bracket of x, Hamiltonian vector field of f, and Hamiltonian vector field corresponding to g, and then xh plus the same, but with first with g and h, so with f, let's write it in the correct order, and xh, and then with g, And finally, with a minus sign, omega applied to the bracket of x f, sorry, here xg, sorry, not f, but g, and h with xf. Now we need to use, this is close to the solution, but we need to use another one of the properties here, which is that by definition of the Poisson bracket, we know that this is the Poisson bracket. For instance, this expression here is a Poisson bracket of G and H, basically by definition. So we have here, we are going to translate here this omega applied to two vector fields to a Poisson bracket of two functions, which we know is true by definition of this Poisson bracket in a symplectic manifold. And on the other hand, we are also going to use that. This is maybe a more critical property that for sure you also know, that is that a Lie bracket of two Hamiltonian vector fields can be written as a vector field of a Poisson bracket. So this will be exactly equivalent to this expression here. And I cannot remember if Eva proved this property, maybe not, but it's a property that you can prove.
No, I didn't prove it.
Well, it's a general property. It's like a well-known property.
But it's easy to prove. I mean, well, it's the exercise that we can even leave to the students is that in order to check that both are the same, okay, you can check it by applying to the differential, to any differential of a function. Let's say f, okay, and then what you observe is that one of them, applying the Hamiltonian vector field to the differential of f, becomes the bracket by definition. Okay, by the definition that we have done, but this is something that I observed, that the bracket is the same as the Hamiltonian vector field of the first function applying to the differential, and then you apply to the second part, and then you check that it's the same. So it's an exercise. So this,
exactly.
Indeed, it's an exercise that we could add to the next list. That's a good idea, yes. Maybe. Or, yes. Well, I don't know, to the exam. There is no exam of the course. Chung,
there can be, maybe.
You didn't tell me if we should do an exam to the students.
Well, yeah, perhaps no exam.
No exam, yeah. That was my proposal. I saw the faces, even if people don't have the camera, I saw some people trembling in their house. Oh no, I have to do an exam at 10 p.m. in China. This is terrible. No exam. Okay.
Let's say that no exam, and at the end, the last day, a surprise exam, and then everyone will be.
Now, the last day, there is a surprise. We don't know still what is the surprise, but true. We will organize a surprise. Okay.
So this is. Thank you, Eva, for this clarification. I didn't know if you proved, but it's left as an exercise for the reader or the viewer. And let's end this proof, because since now we have this property that we can use, we can write this equality now with the 6 terms written as a last form, which is close to Jacobi's identity in the form we had written it before, in which all the terms appear in this circular way we are looking for. So it's clear that we are proving it in the right way. This is the sum with alternated side in this precisely in this circular way of permutating them. And here f and g. And on the other hand, the other 3 terms now are minus omega applied to this Hamiltonian vector field of the Poisson bracket. And now also with circular permutation of the terms, so an alternating sum. So we can see we are really close, really close to the solution. Here we have the bracket of A and H with the Poisson vector field corresponding to G, Hamiltonian vector field corresponding to G, and finally we'll have the Hamiltonian vector field of the bracket of G and H with X of F. We use again here this property we were using before, which is that this is simply the Poisson bracket of the function that gives us a Hamiltonian vector field with where we are applying to. So directly, this gives us the Poisson vector field we are looking for in Jacobi's identity. We will do this for the first three terms, and for the other terms, we know that this, for instance, is the bracket of these two functions: the function that comes from the Poisson bracket here, and the function that comes from directly from H. And observe, well, you can already see that it will be true, but observe that there will be repeated terms. Each term will appear 2 times. Since we change the order, well, let's write it first, and let's make the observation when it's all written here. But clearly, with these properties, the solution is almost direct. So we have here G with F and H. Sorry, with a minus in this case, plus H with F and G, minus F and G with H, plus F and H with G, and minus G and H with F. Now here we can make the observation now, since it's clearly written. First, let's observe that this term, I will take the red one, this term and this term are the same with a minus sign, but in the changed order, and by the symmetry of the Poisson bracket that we already checked, we know that this is equivalent. No, this is equivalent with a sign to plus F with the bracket of G and H. So it is repeat. It happens the same with the other 2 brackets. So we can write now with total convincement that we have 2 times each of these 3 terms. We have 2 times F, the bracket of F with the bracket of G and H, plus the bracket of G with the bracket of F and H, plus the bracket of H with the bracket of G and F. Sorry for this lack of space. But at the end, what we know? We know that this expression, from the beginning, we knew that this expression was going to be 0. So basically, we have proven at this point, we have ended the proof that Jacobi's identity is satisfied in this definition of a Poisson bracket from the symplectic form only. So we have proved the 4 properties that the Poisson bracket can satisfy. So we have proved that from a symplectic manifold, we can define a Poisson structure. We can, if we have a symplectic structure, we also have a Poisson structure. And this is exercise 113. If you have any, this is general. If you have any doubt at any point of the exercise or on the next exercise, please just interrupt and ask us, Joaquim and me, and we will try to solve this question. I hope this exercise is clear. And I pass the pen to Joaquim, and he will continue with next exercise.
Thank you. As Pau said, if you have any questions, just feel free to interrupt us or write in the chat. Otherwise,
or if there are volunteers.
Yeah.
Or if there are volunteers to do this exercise, well, I mean, you are super well prepared. You are like the army, right? Ready, but well, I know that some people have pre-contacted you to go on the Blackboard. This is good, so they know, so it's prepared. But if somebody spontaneously wants to make a comment or go on this virtual Blackboard, this infinite Blackboard from Barcelona to China and around the world, because I see Joe Palmer connected. This is nice. So if you want to go on this infinite Blackboard, you are welcome. Okay, otherwise let's go on with the plan.
Yes. Let me share my tablet screen. Okay. All right. So the exercise is number 1. Here it is, and it's actually a pretty simple exercise. I have to say the exercise it actually has a typo in this version. Oh no, I think we said that we have to say this was a test of your attentiveness. So
this was a trap. You had to
yes.
notice it.
Yes. So here we are with
Some people
the
notice
statement of the sorry.
So even some people in the audience noticed that there was this error. This is good. I'm muted. It says, okay, I'm muted or not? Oh, you can hear me. Okay.
No, we can hear you.
Okay. Yeah. So people are following the course, are sending comments, which is very good. Okay.
Yes.
Perfect. Let's go on.
Indeed, the right version. Oh, for some reason it's smaller, but that's fine. The right version. It's like this.
Right version should be bigger, Joaquim.
Yeah, but
this infinite blackboard.
Yeah, but nevertheless, we have the planar circular three-body problem. So the setting must be already familiar to you. We have get some space. We have 2 big bodies and a small, assumed to be massless body that is attracted by both of them, and thus we have the problem. The problem itself, it's just a change of variables for the standard symplectic form in R4 in this case with the polar coordinates. So we can do this just right away. So the symplectic form, we know which one is it. It's the radial coordinate with its momentum, as in the second version. So that is the angular coordinate, and the angular coordinate paired with its associated momentum. And the McGehee change of coordinates is non-canonical. So the resulting, obviously the resulting symplectic form will be, will not be a symplectic form precisely. So the McGehee change of coordinates, sorry, works like this. We take, oh, I don't know why this is moving. Okay. Well, whatever. Works like this. So I will try to get rid of something. Okay, never mind. Thus, we need to apply this change, but we don't have an associated change in the momentum. So actually, we just need to apply the derivation to this coordinate, and we get the solution already. So this is indeed working like this. And the important thing is that we are not changing any other coordinate. Yeah. Okay. What? Okay, this is annoying me a little bit because I want to write more, but I'll just get rid of some things here. What I wanted to, so this is the exercise itself, but what I wanted to call your attention to is how these new coordinates, these x, p, r, alpha, p, alpha, they have actually a different domain than what we are used to with the polar coordinates. And this is the point of the change of coordinates, really. Because when we apply the change from Cartesian coordinates, from the x, y to the r alpha in this case, we always have this small caveat that, oh yes, just recall that r equals to 0 the 0 point is not included in this change of coordinates because the change of coordinates breaks down here. So when we look at the spatial coordinates here, the R and the alpha, what did this happen here? Okay. When we look at them, their domain is actually,
okay.
Sorry, this is kind of annoying. I will just start a new note.
Marcello just connected. Joaquim, you can ask Marcello anything you want about the restricted free body problem. He's an
Nice.
former student of Andreas Nauf. He knows everything of the book, right? Of the book of Andreas. So, no? Should I tell Andreas that you did?
I have both the German and the English book here, so I can always look it up. Don't worry.
Yes.
Nice. So what I just wanted to comment is that in this case, the domain of this change of coordinates, it's like this. The open setting here. So we are not including the 0 in this particular case. We are looking, let's say, at this is the R coordinate, this is the alpha. Okay, we are looking at everything that goes in this small interval, but we are excluding what lies in 0. However, when we do this change of coordinates, we actually want to include the x equals 0 in our problem. We are interested in that. So our domain in this case includes 0 to infinity times the same domain for the alpha. And this means that we have here the x, here we have the alpha, let's say, here we have 2 pi, that's fine. And our hypersurface, the z in this case, it's this. Of course, I'm not representing the momenta in here, but that's fine. They're just copies of R, each of them. And what is interesting is that if we look at this as a B3 symplectic manifold or as a B3 submanifold, whatever you like to call it, we have actually a continuity in the dynamics. We can have a dynamic happening here in the standard part of the manifold, let's say, but we also have dynamics inside of the critical set, which make no sense from a physical point of view, perhaps. But the interesting thing is that we can study the interplay between both of them. So the point of the exercise was to have an opportunity to expand a little bit on that.
This is fantastic. You said it, you expressed it much better than I did. And this is a very important point of thing. This is a fundamental point for people working in celestial mechanics who are now looking at this kind of change and appreciate the fact that we identified this with some structure like its B3 structure, because this is what they do. They are interested, as you say, in this interplay. I couldn't have found better words than you did. Very good.
Yeah, just to point out that this interplay, what allows us is precisely to study things that go towards infinity, because I didn't comment it explicitly, but x equals to 0 is the running towards infinity of orbits. So escape orbits in this case.
Yeah, for instance, one may have, periodic orbits at infinity and try to understand if they extend in a neighborhood. This is something that still we didn't, I think there is something there, okay? Because, well, people have been working with different sections and have been using this existence of periodic orbits and this idea of Poincaré of perturbation. Now I'm talking ahead of what we are doing. Okay, I'm talking for Marcello and for Chung. But still, within this new framework, these ideas have not been yet put in practice. And this is a plan. This is something that we plan to do. This is also related to the thesis of Joaquim. Joaquim is an expert in this, though he doesn't look at the KAM point of view, but he looks for periodic orbits with a very complicated object called Floer theory, Floer complex. Okay. Sorry to interrupt.
No, that's fantastic.
I make
Does
propaganda.
anyone does anyone want to ask anything about this first exercise? Otherwise, I will jump to the next one.
Well,
Yeah.
I just wanted to say that I don't know if she's here connected, but we received, just to say thank you to a solution that we received, that it was correct, even with the trap included, but it was well done. So I think it was Jiayang Lee who sent us the solution, and it was correct. So thank you to try and to.
So Jiayang, are you around?
Thank you.
Okay. Do you want to go to the infinite blackboard that goes around the world and write something?
Sorry, I don't hear it clearly. So please repeat.
Yes, I was asking, Pau was saying thank you because you sent the resolution of the problem. And we were asking if you wanted to go on the blackboard. Do you want to say something?
I want to ask. I don't understand. What's I don't understand. What are you talking about?
You don't understand what we are talking about.
Talking about.
Talking about I think you did it correctly. So maybe since Joaquim also reproduced the same proof, I mean, it's all clear for everyone. Just wanted to say that thanks, but I think that it's not necessary that you come to the blackboard, but you did the correct proof, the same as Joaquim did.
And thank you for participating.
I don't know what's the meaning of the coordinate.
The meaning of X.
Yes.
Oh, yeah.
The meaning of the incognate. Yeah. This is what Joaquim was explaining. Joaquim, are you going to?
Attempting to.
Okay, I let you read.
No, yeah, feel free to comment about it. I just wanted to have it here written inside. So yeah, the idea of this change of coordinates is that we are originally in the polar coordinates, which is this one on the left, and so the polar coordinates have this have the variable r, which allows us to look at a variable that talks about the distance, let's say, from the center towards infinity, and the motivation, let's say, to use x, this change of coordinates that only affects this first spatial coordinate, is to invert this. So we are bringing infinity to 0. This means when x approaches 0, our variable r tends towards infinity, and obviously the other way around. So when r approaches 0, x goes to infinity. So we are kind of inverting the whole geometry of the problem. And the utility to do this, the motivation, is to study the behavior of this problem, this circular restricted three-body problem, planar as well, to study the behavior of this problem when our third body goes really far away from the two others. What happens when our body is really just going away from the two primaries? What's the behavior? What kind of orbits can bring you towards infinity? We call them escape orbits precisely because you're kind of escaping the gravitational pull of the primaries. So that's the kind of phenomena that you would like to study using this change.
Okay. Thank you.
You're very welcome.
Thank you for the participation.
Yeah. Okay, if that's all right, I will jump to the next exercise.
Yeah, just a comment, like probably since you were interested in celestial mechanics, I don't know if McGee did it before Penrose, but in general relativity literature, there is such a trick known a la Penrose, which is known as Penrose diagram. So mapping asymptotic infinity by conformal transformation to finite distances. So basically plus minus infinity are mapped to finite distances, Scri plus and Scri minus, which creates a hexagonical diagram known by Penrose diagram. So for Minkowski space, for asymptotically ADS or DS space, like whatever be the space time, you can do a conformal compactification, mapping infinity to finite distances. And in doing so, all your computation become much more tractable than so.
That's nice.
I guess
so that's nice. Can you provide us later on, not now necessarily, or can you send us an email with this reference? Because
sure.
Yes, please.
Sure. Yeah, it's there in the 2 volume of Twisters and that by Penrose, means in much more, and also Hawking Ellis, that fantastic book on, yeah, but I can, yeah, sure, means it's same in the spirit. So sorry for
but maybe they didn't say that there was some kind of a structure. Maybe we can find a hidden B structure there. There is also the notion of B metric, and this is maybe a good motivate. I mean, I'm looking for physical motivations for more examples.
Yeah.
So this is maybe what you are providing, Raju, is very interesting. Yeah.
Sorry for interrupting.
No.
Thank you.
That's very interesting. Please send us the reference. We will be interested. Okay.
Great. Thank you.
Okay, great. Now, let us go for the next exercise. I think I have it around here. Well, this is the third one, so that's not the one. Well, we are doing exercise 2 in this case, so we are jumping to quite a different subject, which is trying to understand what is precisely this B tangent bundle. So what do we mean when we talk about this? Oh, okay. Sorry. What do we talk about when we talk about the B tangent bundle? Because this is actually kind of a tricky subject. So we included this exercise to have one of the simplest examples where you can really understand what's going on with this topology. Let's go to even a simpler example. In this case, what happens if our manifold is just R, the line R? This is M. Well, in this case, you can basically only have one possible choice for hypersurface, which are points in the line. So perhaps you can pick just one point as a hypersurface in this case. And the question is, does the B tangent bundle in this case have any relationship with the tangent bundle, the relational tangent bundle, which in the case of R is really not that complicated. It's just R times R. It's the trivial tangent bundle in this case. So what happens in the B case here? Well, I don't know if Eva, did you mention the Serre-Swann theorem? How is the bundle constructed?
Yes, I mentioned this, and I So what I did is that we need a C-infinity finally generated module. And I put the example, but you can do it again. I put the example of taking local coordinates around Z, vector fields that are tangent to Z and work it out. So I think it's good if you were thinking of doing the computation again, I think it's a good idea. Because I tend to rush and people sometimes cannot follow.
Okay. By the way, before I forget about this, we are posting the solved problems as well, the text of all the solved problems in the web page, so you will be able to read carefully through the solutions of everything.
The solutions are still not there. We wait for the end of the class.
Yeah, of course.
So nobody can go and do the exercise by copying the solutions.
Well, we could allow for this. They could
exactly. We can do whatever we want. We are free. Yes. That's good.
Nevertheless, the main idea to define this bundle is the MaterialMelrose theorem, and the MaterialMelrose theorem, in practical terms, gives us an equivalence under good conditions between vector bundles on a given manifold and modules on a given manifold. So in this case, you can study the tangent bundle, for instance, of R. You can understand this as this vector bundle, or you can study its properties by studying its module of sections. So the module of sections of the tangent bundle, which in this case is actually quite trivial, because the sections of the tangent bundle to R, they're nothing else, they're just the functions on R. Or you could think that it's generated by the constant function 1 and generated over C infinity of R in this case. So this is basically C infinity of R. But you can go to more complicated things. And the main property that you can think about is the most essential one, being parallelizable. Our vector bundle is parallelizable. This means that it is generated precisely by as many vector fields as the rank of the vector bundle. So in order to think if the B tangent bundle is isomorphic to the tangent bundle in this case, we can ask ourselves how many generators do its sections have globally. This is the important thing, because locally you can always find as many generators as the rank, but globally you usually cannot. You may have this property only if your vector bundle is parallelizable, if it's trivial. And in this particular case, we can see that for the line, for R, this is the case. We can pick whatever function we like that vanishes R at this set and just multiply it by this. So we can think that, okay, the sections of my B tangent bundle, they are just the function, let's say, if Z is 0, for instance, you can just pick the function X. It's just the generation by any other function. So this is not particularly interesting in this case, but it gives us a guideline. So we have a case in which we have an equivalence between these vector bundles because their models of sections are equivalent between them. Because of course they are not identical, but because the generator is different, but they are isomorphic. You can just send one generator to the generator of the other, and there's no other trick. So we can jump to the second most interesting example, which is the circle.
Sorry, can I ask you something before you go to the circle? So if you
Yeah,
have 10 points on the line, so say instead of just that X equals 0, you have 3 or 4 points. Would that be then, what would you pick that? The product of X minus the point for all of those points, or summing them around?
Yes, just checking the polynomial that vanishes in the finite number of points. Thank you very much for that point. In this particular case, in the case of the line, if you take more points, you can just take a polynomial that vanishes at all the points.
That's a good point. Maybe we can add this in the resolution of the problem as a remark.
Yes, that's very good.
Idea.
I just wanted to add this prelude to understand the philosophy here, but yes, this is an excellent point. So yes, in this case, the generator, as you said, it's the function x minus z1 times x minus z2 times x minus z3 generated by all the functions. It's important to take care that this generator vanishes transversally. This is the most important thing. So you want the function not to vanish. Well, you want it to vanish like locally. It has a linear behavior. You don't want any tangentiality in this case. Yeah. Okay. Now, if we go to the circle, which in this case is not perfect, but that's all right. We can now ask ourselves, okay, what happens if I take points in the circle as my exceptional hypersurface? And we can start with just one to investigate this. So I'm just taking this Z. Later, I will check more of them. Here in Z, I have a similar behavior. Again, this is just one-dimensional, so it's not too complicated. The vector bundle is actually trivial in the tangent bundle case. So this is basically isomorphic to S1 times R, which means that its set of sections is just generated by the constant function 1. It has one generator. So for the B case, we have the B tangent bundle. We can think if we can find one generator. We could find, at the very least, we can find two probably, but we are interested in seeing if we can do with just one. If we can do with just one, then the vector bundles are isomorphic. Otherwise, they are not. So we could assume, okay, what happens if I have just one generator? Let's assume that the sections of the B tangent bundle of S1 are generated precisely by just one. I will express it as F because in dimension 1, the sections are just functions, actually. It's infinity of S1. I have not included the S1 in here. But now we have to ask ourselves, what are the conditions on this function? Well, it has to vanish exclusively at Z, at the point Z. So we need to have F at Z equals 0, and otherwise it must be non-zero. So F of X must be non-zero for all X that are not Z actually. So let's see that this way. But moreover, it must vanish transversally. And the transversality in this case, if I sketch a picture in here, if the horizontal line is our zero section, what we are saying is that F must cross the zero section in this case. So this is 0, this is F. So at the points in which it vanishes, it must change sign. This is the most important thing. F must change sign each time that it crosses over 0. So if we take all of this together, we see that we cannot find this. It's impossible because if we take S1 and exclude Z, we have a connected manifold, we have a connected variety. However, if we separate the parts in which f takes positive values and negative values, we can do this because f is just a function. It is evaluated in just one coordinate and you get one number. This is impossible, actually. If we separate the positive and negative part, we should have two connected components, and we must have at least one change of sign. So I don't know if this explanation is completely clear, but this is a proof that we cannot have this f. This f cannot exist precisely because it must change sign in this case. However, if I go on and take a second point in here, let's take, just for simplicity's sake, let's take an antipodal point, just because it's easier for me. So if I think of the circle as being just the interval from 0 to 2 pi, and I'm identifying, I could take this first point to be the point 0, and here the point pi. Well, I can find a generator here. This is pretty easy, because we can have gamma of the B tangent bundle to S1. This is just generated by the cosinus of x, for instance. So again, this tangent bundle is actually isomorphic to the tangent bundle at the original manifold. So yeah, that's very nice. And now if we try to generalize this, the only thing that we need to take into account is when can we find this generator and when can we not. So the complete solution to the exercise, if you generalize this and take more and more and more points, you only depend on the parity of the number of points that you are taking. If the number of points that you are taking is odd, then you find yourself in this first case. It's impossible. The number of positive connected components and negative connected components doesn't match up. Otherwise, if you are in the even case, you are as in the case of 2 points. You can always construct a function that vanishes at the right points and generates the whole B tangent bundle. Well, the sections of the B tangent bundle. Are there any questions on this?
I'm not a student, but yes, I'm a student in some sense, no? Because you are the expert on B cohomology, Joaquim. And I wanted to ask you.
We are all students all our life as researchers.
So you mentioned that a necessary condition was that there's a change of sign in the point Z where it vanishes. But I was thinking it's not a sufficient condition, no? Because you can have a change of sign, but even you can be tangent, like
yes.
x to the power of 3, for instance, no? So you have to ask for more conditions that I imagine they're more complicated. Well, intersect transversally,
yes.
no, basically.
Yes, yes, you're completely right. And in this case that we are in dimension 1, this is pretty convenient for us, because in dimension 1, as I commented, the sections are just functions. So actually the transversality condition, now you have the opportunity to see my handwriting. Transversality. It could be worse. It just gets translated to the fact that the first derivative is actually non-vanishing. So transversality in one dimension, which is kind of the toy example, translates to the fact that f prima at the convenient point is non-vanishing. But yes, it is, as you said, it is a necessary condition, not sufficient.
Thank you.
Excuse me.
Mm-hmm.
First, you introduce the tangent bundle R1. I want to know is there any difference between B tangent bundles S1 and B tangent bundle R1? If it,
yeah, tell me.
He's asking if there is a difference between the B tangent bundle of R and the B tangent bundle of S1.
Yes. If it is a circle as S1, I want to know, is there any difference?
Yes. So in the case of R, which I think I have here.
Yes.
Yes. So the result is different because in R, you can pick Z to be a collection of finite points as big as you want. And we are only considering this as an example. So, and whatever you choose, whatever collection of points that you choose, the B tangent bundle is the same. It does not depend on the number of points that you choose. It's always the trivial one. However, yeah, tell me.
Gamma B tangent bundle are some points in the line.
The gamma of the B tangent bundle are the B vector fields, the vector fields that vanish or
some points in the line, right?
Z are the points in the line. So Z is the in the language
so
of
maybe what is not clear to her is that gamma is the sections of this bundle. Okay.
Yes.
And then the notation gamma. Okay, that was clear. And then the notation gamma, as Joaquim is explaining, the set of sections of the bundle is what we define as B vector fields, which are the vector fields that have to be tangent to the object that is below. In the case of the line, and in the case of the circle.
Yes.
You see? And then in the circle, it's tricky, right? Because, well, this is what Joaquim has been explaining. Like, there is this difference between, I let him explain everything. I shut up.
Yes.
No.
Thank you.
Thank you. No, let's listen to the explanation of Joaquim, that he was doing it very well. I was just trying to say the notation just in case it was not clear. Let's listen.
You're absolutely right. I had not commented this notation of the gammas. The gammas are the sections always. So in the case of the tangent bundle, the sections are the vector fields, and the B tangent bundle are the B vector fields. So you are considering different objects in a way from an algebraic point of view. A priori.
Yes. Yeah. Thank you.
Yeah, so just to reiterate, in the case of the line, it does not matter how many points we choose. The B tangent bundle is always the same, and it is isomorphic to the original tangent bundle. However, in S1, it depends on the parity of the number of points that you're taking. If it's even, you have an isomorphism. Otherwise, you have a different vector bundle.
Yes, thank you.
So exercise number 3, I won't solve it right now, but you can see how you can solve it from this one. So just using the results that we explained here in exercise 1.2, you can I think you can easily apply this to 1.3 to see when can you have a B-symplectic structure and when you cannot. Okay, so I think I have used enough time. So, Pau?
Yeah. I will now jump to some maybe more applied and on some exercises where we have to do some computation. I'm talking basically about 3 exercises which are kind of similar, which are exercises number 10, 11, and 12. And at this point, I wanted to thank another student, which is Pablo, which also sent us some of the solutions in for instance, the solution of number 10 or number 11. And I wanted to ask him if well, thank you, Pablo. And if you want to do, I think you have another way. Maybe if you want to do it, it's not necessary that you handwrite, but you can project it, you have the solution. So if you want to do, for instance, number 11, you can do it now.
That's great.
And I will complement it with
here on the infinite blackboard.
Yes, it's a blackboard that goes to Murcia, to everywhere.
It goes to Murcia, and in Murcia we have Pablo, but Pablo, we don't see you. We see a black image.
Let me try to see if I...
But we can hear you.
Okay, that's fine. Well,
we can hear you
very badly.
Very little, yes.
Right.
Could you adjust the volume of your microphone?
me for whatever reason. I think is it better now?
Much
Yes,
better.
This is great now.
Okay, fine.
Your image is quite dark. It's completely black.
Can you see?
Okay, there we go.
Is it now?
Yes.
Okay, fine.
Hello.
Hi, Pablo.
Nice to see you
Hello.
again.
Nice to see
Thank you
too.
for contributing to this problem session. So Pablo is going to do one exercise, but he did a lot of the exercises of the list, and he's participating actively in the course. So Pablo, you can introduce yourself and you can explain exercise 11 if you want.
Okay. Hello, I will try to share my screen. I think, are you seeing my screen now?
Yes.
At least, okay. So I want to thank Eva and Pau for the support given so far, because it's been, I also have tried to do and written exercise 1.4, but we have a minus sign that it's dancing, and it's been sort of a small nightmare to figure out where it's gone, the minus sign, but well, we'll figure it out. At the moment, I will be trying to do exercise 111, which is close enough to exercise 110, except the Poisson structure does not split as a sum of Poisson structures in every manifold. But in the end, it sort of boils down to a computation, which is you have a bivector field on a manifold. To check if it is a B structure, you have to check first it is a Poisson vector field, and it satisfies Jacobi's identity as a consequence, because the rest of properties are trivially satisfied. And you also have to check the transversality condition. So is there any comment? Or,
Oh, this is good. Maybe
Okay.
Can you make it a bit bigger, the screen?
I can. Is it
Perfect.
fine now?
Oh, yes.
Okay.
This is even good for people who are older than 40.
Okay. Sorry. So it's just given that we are given the structures in coordinates of S2 and T2, which are angular coordinates and height plus an angle, we will just carry the computations in these coordinates. And actually it's sufficient to do it in these coordinates because these charts cover almost the whole manifolds. So we can extend the results by continuity of smooth functions. So we have these expressions. We can first notice that if we take this wedge over here and develop the sum, we are given the first Poisson structure plus the second Poisson structure plus an additional term, which is the term that doesn't allow the structure to split. So we can just start computations. Jacobi's identity, we compute the Schouten bracket. And by bilinearity, we can just take this term plus this term and develop the sum. Here, here I have used graded skew symmetry to swap a term that well, this term was actually pi1 plus pi2 contracted with this term, or Shelton bracket with this term, plus the skew symmetric one, but we have graded skew symmetry, so there is a 2 because these bivector fields have each 1 degree 2. And we first start by simplifying this term over here, and we could use, if we had proof exercise 1.10, we could use exercise 1.10 and say, well, we have already proved this because S2 is a compact radical surface and T2 is a symplectic manifold, so it has to be 0. But we will try to sketch the argument that we would have used had we proved exercise 1.10. So we can expand the bracket as well, doing the same thing that we have already done. And we have the first 2 brackets are 0 each because we are assuming that pi1 and pi2 are Poisson structures on their given manifolds. So this is the condition that they fulfill for being a Poisson bracket. This we have by definition or by hypothesis. And now we are left to check this Shelton bracket, but we can use some geometric intuition and we can formalize this using the equivalence between bivector fields and derivations. But the intuition, if you want to think geometrically, would be that pi1 is a vector field or a bivector field on S2, and pi2 is a bivector field on T2. And when we have the manifolds, we can lift these bivector fields to the total manifold via the inclusion, the canonical inclusion. And Shelton bracket is sort of an extension of the lead derivative, which is a derivation. And derivation means taking the flow, or at least computing the pullback along the flow. But notice that vectors in S2 generate a flow, or if you want to think coordinate-wise, a vector which only has components in S2 generates a flow which does not change coordinates in T2. And the same thing, when you have a vector or a bivector in T2, the coordinates of points in the total manifold in S2 times T2, the coordinates of S2 that do not change. This is speaking in formalizing a bit in charts for the intuition, but this is the intuition. And as the Shelton bracket is an extension of the Lie bracket, a derivation, the flow generated by pi1 will only change functions and vector fields and such things defined or with dependence in S2, not in T2. So well, you can sort of have this. I think I explained myself really poorly, but this is the intuition, and you can plug this in the Shelton bracket, which only contracts individual terms of the first bivector with the second bivector. And using this intuition, you can see that it vanishes. Another way is, as was suggested by Eva, is to use the equivalence of bivector fields and by derivations and just see that the cross derivatives vanish. And we are left with these 3 terms here. And unfortunately, we just have to compute them because of this cross dependence of H, which is a coordinate in S2, and θ1, which is a coordinate on T2. We just plug the expressions of the Shelton bracket. This is 0 by skew symmetry. This one is 0. This one is 0, and this one is 0. And if this one is even 0 because of skew symmetry here, so it's just 0. And you can sort of do the same thing, which it's with each term, they all vanish. It's just a matter of doing the computations. And so we have that this Poisson structure has a Shelton bracket 0, and thus does define a Poisson structure because we have Jacobi's identity. And now, regarding transversality, we have to compute this map. In this case, total dimension of the manifold is 4. So it should be 2n, in this case, n equals 2. So we have 2 Poisson tensors. And instead of carrying the computations, I have just used the trick and say that in order to have this result, we must have as the resulting multi-vector is in dimension 4, and our manifold has dimension 4, we have to have here coordinates which do not repeat. Each coordinate that repeats will vanish. So I can just start by computing terms. I can contract this one with this one will vanish. With this one, it will also vanish because it has H dependence, and it will not vanish with this one. Similarly, you can compute the second one, see that it vanishes with each other. And finally, you can contract this one with every other and see that it does not vanish here. And finally, to simplify the result, we use, yet again, graded stereosymmetry. You could say that this should cancel out. It does not, because we have a bivector field with a bivector field, and when we exchange the wedge here, we have -1 to the power of 2, so it is a plus sign, and we end up with this. It is these two over here that appears. So this is the map, and transversality in this case is obvious, sort of obvious, and you just have to observe that the height function, or twice the height function, has full rank at the points with height 0, and it has full rank indeed everywhere where it is defined in this chart, because well, it is linear. So we have transversality, and as I commented earlier, every expression that we have found here has been local, but it is almost global, because the set that we do not cover has, well, the set in which we cover these expressions is dense, so we can extend by continuity, and we can say Schouten bracket is 0 everywhere, and transversality is fulfilled everywhere. So we finally have that pi is a B Poisson structure, and it was just a matter of computing things. Have it been clear enough?
Yes, I think really clear.
Really clear.
Yes.
Yeah, that was excellent. I don't know, maybe it was a bit quick. I mean, for me it was very good, but if people,
maybe
I mean, quick. I'm very glad, Pablo, that you got all this already, this master of Poisson. That's amazing. Congratulations, this is very good.
Thank you.
But maybe it was a bit quick for the others. I don't know, do you want to ask any question to Pablo?
So I only wanted to add, Pablo, that you could, maybe from a physicist point of view, that quantum physics point of view, you could also say that since you take coordinates and you can see at a glance that they commute, not from at the point where you arrive to the Lie brackets, not to the Schouten bracket, but to the Lie brackets, you could say, okay, they commute. The reason is that you can see it as a commutator, and you can say, okay, they commute. I can see that since these variables in all the brackets commute, we know that all of them are 0. From this would be more like from a physicist point of view. What do you think?
Yes, like... indeed, you could see this physical point of view, and the geometric approach is what I commented earlier, because, well, this is a physicist point of view, and everything sort of, this physicist point of view has to use charts and coordinates as well. Well, it sort of has to, because we are using coordinates which are, you could say that you may not use coordinates because coordinates are local functions, blah, blah, blah. But in the end, you are using coordinates. And indeed, it is this thing I have said here, which has been a lot of blah, blah, blah nonsense, is really easy if it's less elegant, but you can just plug coordinates and say, well, I have already said this, Schouten bracket just takes elements of this, this bivector here, and contracts contracts them with elements here of this bivector field. And then you have more extra terms, which are these ones, but in the end, you sort of have to worry about the Lie bracket. And as the functions that we are using are coordinate functions and are, well, almost coordinate functions, because we have this HR here, this H here, but H has dependence with H, so it's fine. Are almost coordinate functions. You can just sort of compute the Schouten bracket without looking at it. It just all vanishes, which is what I have said earlier, that if you only focus on these Lie brackets throughout the whole expression here, you can clearly see that the Schouten bracket has to vanish. And this is just blah, 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 to check that it actually vanishes. But if you are lazy, like I am, because when I proved this, I didn't compute the Schouten. Well, in this case, I computed the Schouten brackets, but in 1.10, I didn't compute the Schouten brackets because I was lazy, and I said, well, it will vanish. I mean, I know it will vanish, and I am lazy to put coordinates and check it, but it will vanish. But I have gone really far from the observation. Yes, from a physicist point of view.
I agree with you that in this case, we have to pass through coordinates essentially because the Poisson structure is defined using this combination of coordinates from the two submanifolds. So yes. So I agree with you.
This is a very rich discussion. I'm enjoying it a lot. Thank you guys, because I think this kind of input also gives people intuition. I mean, some people prefer to work out in coordinates, and some other people prefer to see this, as two manifolds crossing, in this product. So I think the point of view that that Pablo is adding is very interesting to the discussion, and also the idea of Pau, that from a physicist point of view, or I don't know what Raju thinks about this. Raju is our physicist at home. What do you think? I don't know if he's now listening. Raju, are you around?
Yeah, it was an elegant proof. Yeah, of course, coordinate-free notation will be much more elegant, as he pointed out. But yeah, of course, it was much more like hard work. But yeah, I completely followed, and yeah, it was a beautiful.
Okay, so it's Raju approved this resolution of problem.
Perfect. And just a small remark as well. If you are really into geometry, you could say that S2 times D2 is both a fibration on S2 and a fibration on D2. So when you lift these vector fields, you are moving along fibers, and you could lift from two sides the functions and vector fields and everything, and they have to have Lie bracket 0 because one is moving along some fibers and the other one is moving along other fibers. Indeed, right. This is a very trivial fibration, which is a product.
Right.
I think that we should leave as an exercise maybe to find, I don't know, let's think about S3, with the hop fibration, and to write a Poisson structure there, because the coordinates is going to be interesting. But you can use coordinates. You can think is that a Poisson as a fibration. You can try to use coordinates. If you think about the hop fibration, this is another exercise. If you want to think in abstract thing, I mean, in a case here, here the argument of Pablo was very clean, and we could see the transversality in a clean way. Now I'm putting as an exercise, think about the hop fibration. Can we think it as a Poisson fibration, as a Poisson, as the foliation, these fibers, as the foliation? Indeed, well, the hop fibration, usually one thinks in the contact setup, but I don't know. It would be interesting. This is an exercise to think. This is an open exercise. And then in this case, indeed, a good interpretation. I mean, you can do it in an abstract way, but also a good choice of coordinates, like what is called the Hopf coordinates, can be very useful to highlight the abstract point of view also. Or in any case, this was a very interesting participation, Pablo. I really appreciate.
Thank you very much.
I really appreciate that. I'm sure that this sign thing that we saw. Now I don't know what the plan that Joaquim had was to explain himself the proof. I'm sure that this is a misunderstanding of some formula. without clarify. I have sent you before a computation by hand.
Yes, I have
I
checked
don't
it.
know about it,
Yes.
just at the beginning of the class. I don't know if you agree with this.
I do agree, but we can talk about it later.
Okay.
To not interrupt the flow of the.
Yeah, let's leave then maybe Joaquim. I mean, go on. No? I mean, Joaquim, or who is Pau or Joaquim?
Well,
or unless Raju has his camera.
The thing is that we need to look at the clock.
No, we never look at the clock. It's true. Oh, it's 2:30. Class is over. Yeah. Oh, let's go party.
What we wanted to say is
we never look at the clock, and then people. It's true that in China it's a bit late, right? So this is the course. So these people are getting up very early because they have the course of Boris. Now we are competing with Boris Hessing at 7 in the morning. So people have to choose if they connect at 7 in the morning with Boris, or at 9 in the afternoon with the crazy crowd of Eva. I don't know, but they are here.
With both, okay, maybe when they connect to both, I don't know. They don't sleep.
They connect to both, but they should sleep at some point, no? Maybe. Yeah. So I don't know. Yeah, I mean, Raju was about to add a comment. Raju.
Yeah, so if I replace the S2 by T2, so will everything go as Pablo was explaining, like T2 times T2? Will it, because I am thinking of a situation like where it is not a trivial fibration, it could be T2 times T2 T4, but then there is a Kodaira-Thurston-Neal manifold where there are some non-trivial way, it's not just T2 times T2, and whether I can do a similar trick there, like the exercise I can repeat.
Yeah, indeed, what you are suggesting is in the line of what I am suggesting. You are looking for a very complicated example in which you cannot see a clear product in coordinates. And what you are suggesting is to look at K3, no? Which is more complicated than the Hopf fibration. Yes, I think that then the argument, then what I'm saying is in that case, coordinates help. I mean, the actual projection that you take on the K3 is going to be helpful. It's more or less what you are suggesting. I think we are thinking in the same kind of examples. I was suggesting T3 T3 and the Hopf fibration, okay, with fibers as one. And then these fibers, if they are orthogonal to what, can we identify as symplectic foliation there? That was a question. This has a natural contact structure, but it seems it's not integral, so cannot be the contact structure, has to be something else. That was an exercise. And you are asking also about the case tree. Yeah, these are other examples. These are classical examples in geometry, indeed, where indeed the having some good coordinates is good to visualize this kind of transversality. I don't know, Raju, we should think about this. This is a good exercise for the next list, maybe. That's a good point. Yeah, I don't know. I'm going to give the word to Joaquim, who is or Pau, who is now the one who has to speak, because it's true that the time is over officially. I don't know.
Maybe we should do Joaquim will do a clarification of one exercise, I think.
Yeah, okay. Right. We just wanted to give indications in case that you want to work out the rest of exercises. So I even cast into doubt that we need to do another list because there is still plenty of things that we haven't done. But exercise number 9, I just wanted to comment that perhaps it's not absolutely clear what's the manifold in that case. So the exercise number 9 as to compute the B cohomology of the B torus of Radko with 2 unconnected components. And what we mean by this is the 2 torus. So we are in dimension 2, and our exceptional hypersurface, our Z, in this case, are 2n circles embedded in these 2 torus. So with this characterization, perhaps you can work this out if you want. I don't know if any other exercise require clarifications. Has anyone tried and needs clarification?
If not, I just, well, in fact, Pablo already commented it about 1.10. In 1.10, the idea is to notice that we have a structure on R and we have a structure on S, and both are Poisson structures. So we know that short-term brackets them with themselves are 0, and we have only to check their cross shortened bracket, which is also 0, since if you take any chart, and as Pablo explained, by the same argument he used, we can see that the shortened bracket is 0 in every term in the. And then to check transversality, I'm just commenting number 10, since it's really similar to number 12. To check transversality, you have to think that since you already have on R a transversal structure which is transversal to the singular hypersurface in R, when you construct the product manifold of R times S, you in some sense you inherit this, you receive this transversality that you had on R to the 0 section on R in R times S. So you can imagine that as a simple example. I could draw it, but you can also imagine if you have a function, a line which is a curve which is transversal to the x-axis on R2, and you add more dimensions. For instance, you add another dimension to R2 to have R3. If you were transverse to the x-axis in R2, automatically you are transverse to the xz plane in R3. You know, so this is the idea of receive this transversality that you have, for instance, for free in number 10. So the transversality, you can think of it in a natural way, that the original transversality you have only in R, you also have it in R times S with this idea. And then I can comment too that in number 12, the last exercise of the original list, that now it's not the last, but the one before the last exercise, in 1.12, which is kind of similar to 10 and 11. If you want to try, if you have not tried yet and you want to try it before looking to the solution, the idea is the same as in Pablo's resolution and of number 10 and 11, and you have to think about the conditions that we give, that we ask to show that are necessary to prove that it's a proper Poisson structure. The conditions are related basically to transversality. You need these conditions that F vanishes linearly and that the vector field is transverse, both to transversality, and if you do the Jacobi computation to check that the Poisson bracket of pi with itself is 0, you can do it I mean explicitly, because you will see this commutation, with Charles, this coordinate property, that if you have one part of the bracket in some specific coordinates and the other part in other coordinates, you will have for free when you arrive to the Lie bracket of this, to the Lie brackets, the sum of Lie brackets, all of them will be 0. So the idea is always the same, but you need both conditions on the statement of the exercise to prove transversality. You need both of them. Mm-hmm. And I don't know. So
well, in any case, the solutions are going to be posted today. And you can check them out if you have questions. It's true that we reached the time and we should start. Yeah, I mean, I never look at the words. This is my problem. But it's true that it's good that maybe today we just finish 8 minutes late the class. So we make it a 1 hour and a half class as it was initially scheduled. If there are more questions or comments, one thing, I mean, you can keep on sending emails. By the way, Raju, I have already the thing that you asked me for. I'm going to send it to you. I just got an email that Raju asked me for something. I will reply to him personally now, and feel free to send emails. We are happy to get emails, the three of us. This makes us feel that people are following the course, and it was very satisfying experience as first class.
So thank you very much to everyone.
Raju is sending us, that's very good.
Oh yes.
Raju is sending us a very interesting reference where we can find other physical models where these structures might be needed. So yeah, that's perfect. I really appreciate. I mean, for me, it's very interesting. If I have some physical example where I can put my big hands on, that's fantastic. Okay, so it looks like we can finish here the class, no? Pau and Joaquim, and some last words that you want to add.
well, we encourage you we will post the second list next week, and we encourage you to do it too, since it's really interesting also to have this feedback and these contributions for you in the class, and all the questions we can solve during this week. We will do it with respect to the first list or to the second list that we will post on next week.
Exactly.
Yeah, we will respond to your interests.
Yeah, sorry, go on.
No, we just answer to your interests. So
yeah. Thank you very much. Thanks, everyone. Have a nice weekend. Don't forget that now next Tuesday, we are going to start something very exciting, which is we are going to start looking at symmetries of these manifolds. And by symmetries, I mean integrable systems and group action. So I think that Raju is going to appreciate that. And I hope all of you. See you next Tuesday, okay? And we will update today the website with these solutions, so you can have the complete solutions in tech. Thanks to everyone, and special thanks to the ones who have been participating in the resolution of the problems. Pablo, Pau, do you remember the name of the person who just participated?
Yes, Yang Lee also contributed. Yes,
thank you.
Thank you to everyone.
Thank you very much.
Thank you. Okay, guys, see you soon.
See you on Tuesday.
And thank you. I see Joe Palmer is connected. This is great. Hi, Joe. I mean, I don't know what time is it there now, but hi, he says hi. Okay, good night, China. Good morning, Toronto. See you on Tuesday.
See you.
Bye.
Bye.
Adios, Pablo. Thanks for your participation.
Bye.